While the limit definition that we've been using in 2.1 and 2 is useful for finding a derivative anywhere on a function, either a derivative as a function or a derivative value at a point, it is a little bit tedious, so we do have some shortcut rules that can help us find derivatives for different types of functions. So we're going to go through some of those now. First of all, this is another notation for derivative that I did not give you in the 2.2 notes. If we have a capital D and then a subscript X and then something inside here. Now, sometimes it's in brackets, sometimes it's just written normally. Anything like that means the derivative with respect to X of whatever is right here. Okay, so like this first one means derivative with respect to X of N. All right. Also, this is from your book. C, N, and K are all, actually, I didn't use C anywhere. All right, don't worry about that. But N and K are both constants and they are real numbers. X is a variable. So we're dealing with functions in terms of X here. All right, so if we're looking for the derivative with respect to X of N, where N is a constant, well, let's think about what that looks like visually. The graph of Y equals N for any value of N is a horizontal line, okay? And the slope of a horizontal line everywhere is 0. So the derivative of a constant is 0. If we think about derivative in terms of another phrase, rate of change, well, the rate of change of something that is constant is always going to be 0. Next, we have the identity function. So this is the derivative with respect to X of X. So again, let's think about the graph of that. If we have the function Y equals X, that is a linear function, and the slope everywhere here is a constant. Not only is it a constant, the slope is always equal to 1, so the derivative of X is 1. All right, and then next we have the power rule. So this is the derivative with respect to X of X raised to the nth power. Now, a very important thing here is that this exponent has to be a constant. It does not have to be an integer. It does not have to be a whole number. It could be a fraction. It could be a decimal. It could be irrational, but it does have to be numeric. This does not apply for, say, X raised to the sine X, or a variable expression raised to another variable expression, okay? So we will deal with how to take the derivative of those later, but for now, it's important that you recognize that this is just X raised to a constant power, okay? And our derivative is going to be N, that constant, same thing that was from the exponent, times X to the N minus 1. So it's not that we're bringing the exponent down. Don't think about it like that. But we are multiplying by the exponent and subtracting 1 from the exponent to get the new exponent. Now, if you think about what we did with polynomials when we were sketching those, you may have noticed that, like, the derivative of a cubic function was quadratic. The derivative of a quadratic was going to be linear. So when we're talking about polynomials, the degree of the derivative is always 1 less, and this power rule is really what solidifies that for us. So when we get to taking derivatives of polynomials here in a minute, we'll see that played out a little bit more. Okay. This next one says that if we have the derivative with respect to X of some constant K times any function, then we can factor that K out to the front and then take the derivative of the remaining function on the inside. This should look similar to what we did with limits in 1.3, where we used all of those limit properties to kind of break apart a function in order to take the limit of each piece individually as the limit of a constant, or the limit of just plain X to the first. But this says if we have some constant coefficient, we can move that to the front. So say, for example, we're finding the derivative of 7 tangent X. That's the same thing as 7 times the derivative of tangent X. And trig functions we will get to in the next section. All right, next we have a sum or difference. The derivative with respect to X of 2 pieces that are being either added or subtracted. Again, similar to the limit properties, we can separate these with addition or subtraction and take the derivative of each piece. So we would have the derivative with respect to X of F plus or minus the derivative, whatever is there, plus or minus the derivative with respect to X of G of X. So we can add or subtract by taking the derivative of each piece, okay? All right, now this is where we differ from the limit properties. With limits, we could, if we were taking the limit of f times g, we could take the limit of f times the limit of g. In other words, it's not really the distributive property. Don't think about it like that, but it's kind of like we're applying that derivative onto each piece. But this is a big no-no when we get to derivatives. We cannot distribute a derivative to a product or a quotient. Okay, now I'm going to do a separate video where we kind of prove this, or at least explore this, but for now I'm going to go ahead and give you the formula, and that is that the derivative of, with respect to x, of f times g is the first function times the derivative of the second, so derivative with respect to x of g of x, plus the second function times the derivative of the first. And it doesn't matter what order we multiply or add, because multiplication and addition are commutative, but this is the order that I think of it in. And also, just as far as things that we need to memorize, instead of memorizing it like this, it might be easier for you to remember that the derivative of f times g, the product, is equal to f times g prime plus g times f prime. This is, if I'm doing a product rule in my head, this is really what I'm thinking of. I don't think of like f of x times d sub x of g, like I don't think of all of this notation. I just think of it this way. They mean exactly the same thing. This one just matches the notation that's in the book, okay? But as far as what you should memorize, I would think about this one. Okay, and again, I'll do a little bit more exploration on product rule on a different video. Okay, and then for the quotient rule, again, we cannot just take the derivative of the top and bottom. That's one of the most common mistakes that people make. We do need to use a different formula. It's something that can be proven. You're not going to have to prove it. So again, I'm just going to give you the formula. Okay, so, and I'm just going to write this as f over g, kind of this shortcut notation. So if this is the same thing as f over g prime, it's equal to the denominator function times the derivative of the numerator, so f prime, minus the numerator times the derivative of the denominator, and because we're subtracting, the order here does matter, and then over the denominator function squared. Okay, so these are apostrophes, these are primes, that's a square. Okay, you may have heard before a shortcut, kind of a mnemonic device for finding this derivative. And that would be, if we think about a fraction as, we'll call the top high, like the high part, and then the low part. Okay, so if we're taking the derivative of high over low, then one way to remember this is low times derivative of high, which we would say d high, minus high times d low, all over the square of what's below. So when we say it, it rhymes. So low d high minus high d low over the square of what's below. Okay, that's one way to remember it, or you can use this. Either one is fine. So let's do a couple examples. This would be a good time to pause and try these on your own using these formulas. Notice that this first one is a different variable. That's fine. Your derivative just needs to be in terms of that same variable. Okay, so for part A, s prime of t, I'm using my property that says I can take the derivative of each piece because this is a sum and a difference, and then also I'm using the power rule here. So this is going to be 4 times, and then the derivative of t cubed is going to be 3 times t to the second. In other words, 12t squared. You can do that in 2 steps or 1, it doesn't matter. Plus the derivative of 19 times t is the same thing as 19 times the derivative of t, so 19 times 1. And then minus the derivative of a constant is 0. So 12t squared plus 19 is our derivative function. Okay, for this one, I do have a fraction, but this is a big important thing right here. This denominator does not have a variable in it, meaning 2/3 is just a coefficient. Okay, so this is 2/3 x to the 12th, meaning I only need to use the power rule. So y prime is 2/3 times, and then the derivative of x to the 12th I'll write this one in 2 steps this time. So 2/3 times derivative of x to the 12th is 12x to the 11th, or in other words, 2/3 of 12 is 8, so 8x to the 11th. For this next one, I have 2 options. I can either use the product rule, or I can multiply them together and then take the derivative, okay? Just don't break any algebra rules. I'll go ahead and use the product rule this time. So this is my f, and this is my g, okay? So the derivative, so f prime of x, is going to be the first times derivative of the second, so x cubed minus 5x times the derivative of the second, which is 2x plus 0, okay? Plus the second, use parentheses wisely, times the derivative of the first. Derivative of x cubed is 3 times x squared minus derivative of 5x is just 5. Okay, I do need to simplify this. So distributing, I have 2x to the 4th minus 10x squared, plus distributing here, we have 3x to the 4th plus 12x squared minus 5x squared is 7x squared, and then minus 20. Which is 2 plus 3 is 5x to the 4th, and then negative 10 plus 7 is minus 3x squared minus 20. Okay, again, we could do this one by multiplying first, so I'll go ahead and show you that real quick. If I multiply those together first, I would have x to the 5th, and then minus 5x cubed plus 4x cubed is minus 1x cubed, and then minus 20x. So then when I take the derivative, I don't need to use the product rule anymore. I just use the power rule on each term. So 5x to the 4th minus 3x squared minus 20. I do get the same thing. This one probably a little bit more efficient, but we got there either way. For this one, I'm going to use the quotient rule. So the top is f, bottom is g. Okay, so low is x squared plus 4 times d high. Derivative of that is 3x squared minus 5 minus high, which is x cubed minus 5x times derivative of low, so d low is 2x, all over the denominator squared. Okay, and algebra tip, leave this factor. Don't even bother to square it or to evaluate. Okay, so then we have 3x to the 4th, and then plus 12 minus 5 is plus 7x squared minus 20 minus, and then distributing the negative 2x to all of that, we have negative 2x to the 4th plus 10x squared all over x squared plus 4 squared. I'm going to cheat here and do that, okay? Which, simplifying, we have 3 minus 2 is x to the 4th, and then 7x squared plus 10x squared is 17x squared minus 20 all over x squared plus 4 squared. Now, if I could factor this and x squared plus 4 was one of the factors, I would want to do that and reduce, but in this case, I cannot, so I leave it like that. Okay, for part E, I can use the quotient rule. If you use the quotient rule, because we don't have a variable in the numerator, remember that the derivative of that part is going to be 0. It is not 1, it is not 2. But to avoid using the quotient rule, my other option is I can write this as 2x to the negative first, and now I can just use the power rule. So f prime is equal to 2 times negative 1 is negative 2, negative 1 minus 1 is negative 2. So this is negative 2 over x squared. Okay, and try not to leave negative exponents, so go ahead and move that down and make it positive. Okay, last one here. We can use the quotient rule again, or we can do algebra first. I'll do it both ways. So using the quotient rule, denominator times the derivative of the numerator, which is 1, minus numerator times derivative of the denominator, 6x, all over denominator squared, so that's 9x to the 4th, okay, which simplifies to 3x squared minus 6x squared plus 36x over 9x to the 4th which is negative 3x squared plus 36x all over 9x to the fourth, which I'm going to divide everything by 3x. So we get, I'm also going to switch these, so I'm going to get 12 minus x over 3x cubed. Okay? The other option here, if I want to simplify this algebraically, is I can go ahead and divide. So x divided by 3x squared is 1/3 x to the negative first, and then minus 6 divided by 3x squared is 2x to the negative second. Now I don't have to use the quotient rule, so come down here. Using the power rule, f prime is equal to negative 1/3 x to the negative second, and then plus 2 times negative 2 is negative 4, so plus 4 x to the, make sure you're subtracting, not adding, so negative 1/3, which is negative 1 over 3x squared plus 4 over x cubed. You can stop like this. If you want to get a common denominator and add them together, you'd get exactly what we have here. Both of those will work. Okay? And then the very last example, this says, where is the tangent line to this function? Horizontal. Horizontal means a slope of 0. So this is asking us to find the derivative, to find the slope of the tangent, and set it equal to 0. So find our derivative using the power rule and the sum and product rule. So we have 3x squared plus 8x minus 3. And then this is the slope of the tangent, so we set that equal to 0. Okay, and we can use quadratic formula, completing the square, or solving by factoring. I'm going to try factoring first because that's usually the most efficient. If you would like a shortcut for factoring, that's what I'm going through right now. You don't have to use this, but if you have questions on it, let me know. Okay, I'm going to multiply that times that, make that negative 9. Factor pair of negative 9 that adds up to 8 is positive 9 and negative 1. Dividing by 3 here, I get x plus 3 times 3x minus 1. Again, if you want me to explain how I did that shortcut, let me know and I can make another video. All right, so I get x is equal to negative 3 and 1/3. So there are two places where the tangent line is horizontal.